All right. So products over reactants, and then we take it to the power of the coefficient for the balanced equation. Key things with this is if it's a solid or liquid, we make the concentration equal to 1. And we can imagine this, the gaseous particles moving very fast. There's a certain number of moles per liter of the container. Same thing with the aqueous particles. If they're dissolved, they're throughout, they're moving. You have moles per liter. Solid is just sitting there in one place. Liquid, you're only going to have it on the surfaces where liquids might touch or something like that. So we just make their concentrations equal to 1, which doesn't affect the mathematical equation. What's that?
Can you share your screen?
Actually, it's just me talking right now.
Oh, dang.
No worries. But I'm getting ready to, Lily. You're one step ahead of me. How are you guys doing? Good weekend? What'd you guys do yesterday? Did you get everything done you needed to get done? Did the teachers overwork you?
Yes.
Really?
Yes.
I hate to hear that. Is that when the genetics lab came out?
Yes.
Oh, no. Yuck. All right. Let's plug this in. Well, we had a big old meeting yesterday. Took a lot of energy out of me, though. All right, so I'm on the packet, and I'm on page 15, it looks like. I think it's safe to say that you could print this packet out because I'm not going to be able to make any adjustments to it because I don't have time. But I am going to add one worksheet or 2 worksheets to it. So we'll add those to it. But this packet is about as done as it's going to get at this point for this year at least. Is it just the sound of that guy's voice out there? Is it the teacher from across the hall? Is it disturbing you as much as it is me? All right, cool. All right, so if we look, last time we discussed, oh, let's look at this. We discussed the quotient probably last Wednesday or Thursday. So if we take a look, we have SO3, so sulfur trioxide, yielding sulfur dioxide and oxygen. This is the equilibrium constant. Zoom in on that. This is the equilibrium constant. These are the concentrations where we are, right? So we have 0 for the products and 1 for the reactant. Which way is this equation going to go if we have 0 for the products? If the equilibrium constant is 0.230, that means we have 0.230 products to 1 reactant. Do we have 0.230 products currently? No, because we have 0 products, right? So what does that mean? One reaction is going to be favored. It's going to be which reaction? Forward or reverse?
Forward.
Thank you. Forward reaction is going to be favored, right? So we can see that. Let's go ahead and figure out where we are at Q so we can relate it to the 0.230. But if this actually was a question that just said, you know, what's going on, what's going to happen here, by seeing that we have 0 products, we would know that forward reaction. Even though the reactants are favored, we got to have some products at equilibrium. So 0 to 0 divided by 1. And we get 0, which means that the favored reaction, we are not at 0.230, so the favored reaction will be the forward reaction. We gotta make some of those products if we want this relationship. Next one, we have 0 reactants. So what do we know here? What do we have to make?
Reactants.
So Q, I mean, it's going to be undefined, but if we take a look, we know that the reverse reaction is favored. Now, the reason I left these two out is because we're going to be in situations with what we call these ice or rice tables, where you've got to sit there and see, oh, we're going forward or we're going in reverse. If you don't see that at the beginning, then you won't know, what to do with these tables. You don't know whether to add or subtract X, basically. Last 2 times ago, I think we actually talked about KSP. So these are the solubility problems. If you don't know your solubility rules, it's time to make sure you get them down. Nitrates and group 1 elements, these things are pretty soluble. Carbonates and stuff like that, those not so soluble. If you need a list, I think I've got one on the front page, like you can download that and print it out or whatnot. But this is why they're either soluble or not soluble. We know that this is solid, so it does not be incorporated into our solubility equilibrium. We know that KSP here is 1.1 times 10 to the negative 36. So what do you think? Is this soluble or not soluble? Those aren't definite terms. Is it readily soluble? If these are the products and it's 1.1 times 10 to the negative 36, is this a big number or a small number? Small number. So that means that these probably won't be in high concentration, which means that it's probably not very soluble, right? Let's check though. Let's check its, what do we call the solubility product constant? All right, so I'm going to go ahead and make what we call the, this is going to be, I mean, again, you guys, a lot of the ex-chemistry students last semester, at least last year, did not get, this because we were already in lockdown. But this is what we call a rice table. We have the reaction. We have the initial. We have the change. And then we have at equilibrium. And remember, equilibrium, again, is just a dynamic, it's a changing, changing system, but the concentrations of everything remains the same. So we call it dynamic equilibrium because it's changing. You don't have the same iron 3 ions sticking out there all the time. Sometimes they attach to an OH and make, the solid compound. Sometimes the iron here is pulled off and pulled into solution. That's that dynamic ability. But at equilibrium, the concentrations are the same. So initially, we have a certain amount of this. We don't even care. We don't have any of these 2 things, so we put them as zeros. The changes, well, this would be minus X. This would be plus X because it's a 1-to-1 mole ratio. This would be plus 3X. So basically, we did not have anything in the beginning. These start breaking apart. If you want to draw it out or whatnot, you have one Fe3 positive and you have 3 HO negatives. So these start breaking apart. That's why we have 3X of these. For every one of these one of these we dissolve, we get one of these and 3 of these particles. So at equilibrium, we don't care about this again, but we now have X and 3X. These are the concentrations. So if we look, we know that K, in this case, we're talking about the solubility product constant, is equal to products over reactants. So we have the concentration of this guy the concentration of this guy cubed. This is the concentration because for every one of these, we get 3 of these guys. And keep in mind, we cube it. So what do we get here? Well, I want to write this as just x instead of that FE 3 plus. So what does that mean? What is 3x cubed? That becomes 9x cubed times x, which becomes 9x to the 4th. Remember that it's up to you guys to check my math on this because you guys are much better at math than me. Is that right, math guys? Yeah, good. And so we have 9x to the 4th equals 1.1 times 10 to the negative 36. So, well, that looks broken. What is that? Oh, it's just a reflection of the cord. So if we take a look, 1.1 times 10 to the negative 36. We're going to divide that by 9, and then we're going to take the 4th root of it. What's the easiest way to do that? I think it's that. There. So we get 5.91 times 10 to the negative 10th. As our molar solubility. Again, we know that iron hydroxide is not readily soluble, just like apparently copper sulfide. Even this lead chloride, not readily soluble. Is there any that are readily soluble? Yeah, none of these are really, very soluble. Let's take a look at the opposite of this. The molar solubility is given for each of the following. Calculate the KSP. So they give us the molar solubility. So basically that's that X. For every 6.3 times 10 to the negative 18th of these, we got to figure out what we've got here and here. So again, rice. This is 2x. This is x. I'm sorry. These should be zeros, and then they should be 2x and x. I'm jumping the gun. Zero, 0, plus 2x, and plus x. And then we basically have 2x and x here. And again, we don't care about solids, so that's that. We have KSP equals, remember, it is products over reactants, but in this case, the reactants, we don't care. This would be 2x squared, and this would be x. So that equals 4x squared times x, which equals 4x cubed. We know that the molar solubility, or x, is 6.3 times 10 to the negative 18th. So we take 4 times 6.3 times 10 to the negative 18th. And then we need to cube that. Just to make sure, I'm going to put this around my calculator. I'm not sure if it has the ability to do it anyway, but safety precaution. So we get 1.00 times 10 to the negative 51. Questions for that? Morning. No, you just went from the other. I thought you were a new student coming in. You throwing your pancake napkin away? All right. How are we on Le Chatelier's principle? Remember, Le Chatelier's principle basically says if you affect something, that it has to get back to normal. So if you add something, let's say here we're adding NO. So we have too much NO. If we remember our ratio, it is a set number. Now remember that's per like set temperature. But if we add a constant, like if we add more of this NO at a set temperature, system has to basically get rid of NO. The only way to get rid of NO is to reverse the reaction, which means we're going to turn that NO into reactants. That gets it gets confusing if you can't separate in your mind the two different things. Down here, it's kind of fun because they have, you know, a stipulation. We have green and yellow or something like that, and we know yellow and blue make green. So if we take a look, K sub EQ is 1.5, and 1.5 means that we have excess blue. So if it favors the product, we're going to see blue. If it favors the reactant, we're going to see more yellow. If it's right at equilibrium, then, you know, if it's a little bit of both, or if it starts to change to both, we may see that green. So let's take a look. Adding a larger quantity of C. If we add C, that favors the production of blue. Cooling the system. Well, we got to figure out whether it's endothermic or exothermic. So if we take a look, do we know? Where do you see it? Ah, right here. The reaction is exothermic. So delta H equals negative, or if we take a look, that means that heat is on the product side. So if we cool the system, we're pulling out heat. That's going to want the system to produce more heat. So we're going to get blue again because blue is on the product side. Adding a catalyst, initially the system is green. So adding a catalyst, we are going to stay green. Not going to have an effect. Increasing the pressure. All of these are gases. We have two gases on this side. If we increase the pressure of the system, it wants to alleviate that by having fewer moles. So here we have 3 moles of blue. Here we have 2 moles of colorless and yellow. 2 is fewer than 3. So we're going to start to see the yellow show through. Removing B from the system. If we remove more and more and more B, the system wants to make more and more and more B. It is going to use up more and more yellow to make blue. So, I mean, that's one of those things that where it may take a few more seconds than it normally would to think about it. Last thing today we want to look at are these sample problems. 742. All right, we're good. For this, you might want to get out a TI 85 or 84. What's that? They actually did, and then they went to back to the 84 plus. Yeah, not funny. My calculator in college was actually a TI 85. Yeah. Yeah. I have it. You know what's funny is I actually when I was in school, I didn't like to ask my parents. So I purchased my first calculator by myself at a lunch table deal for about $10. And that was the TI-81. Oh yeah, this was more than like 2 Nintendo games at the time, but yeah. The TI-81 came with like this battery backup system, and I don't know if they have that yet. But what I did was, this was probably stolen from, high school kid in my high school for, my high school only had like, let's put it this way, we only had like 300 seats. So we were looking at like 1,200 kids max. But yeah, this made it through 3 years of high school. Not sure how I thought about it back then, but I'm gonna feel bad now. But the TI-81 college, I got the TI-85. Again, this was one of those things where I was in class and that's how I ended up with that stuff. But yeah, this is my major college one. It's kind of funny because I felt like I wrote my name like beyond the batteries, but maybe I just tell you guys to do that because I was always worried about somebody stealing because apparently I got mine unethically. But all you guys need is a TI-84 Plus. And this one belongs to. Who did I steal this one from? No. Yeah, doesn't have anything. This was probably left in my classroom a few years back. Does this belong to anybody? But yeah, these calculators, you want to make sure you do keep an eye on them, even in college, especially if you are a friendly person and you let people into your dorm rooms and stuff like that. Because I was lucky to have both of those the whole time, but that is a common commodity. I had a roommate once that his parents cut him off, and he decided to try to find books and weird stuff to make it through college. Some people are pretty desperate. But what we're going to talk about today is the solver function of this. Is we are not going to bother with the quadratic formula, and the AP exam actually does not require it. So those of you great at math, keep in mind your, what do you call that, your, help on this probably. If you have like x squared and all that, your factorials, what is it, to take out everything. Like for example, if you have to square root of both sides of the equation, what do they call that? Come on, you guys, the math teachers have such cool terms for all this. Factoring, right? Is it factoring? Yeah. Keep in mind all your factoring and stuff like that. So, if we take a look, when 0.4 moles of PCl5 is heated in a 1 liter flask, so right there we have the molarity of that, and equilibrium is established in which 0.25 moles of Cl2 is present. What are the equilibrium concentrations of PCl5 and PCl3? So if we take a look, we're trying to reach equilibrium. We have 0.4 moles of PCl5 to start with, right? So what is that? That's 0.4 divided by 1. So our initial concentration is 0.40 molar. How much of PCl3 and Cl2 do we have to start with? Hardest question of the day. Hayden? Is he sleeping? Should we penetrate his dream?
No, I'm here. I mean, if it's a ratio, wait, no.
Not a ratio. We're not at equilibrium. We're talking about the initial. And this is the thing. This is why I want to draw attention to this, because it may seem more difficult than it is, but we're not, if we look, it's not said anything. It just says we have this heated in a 1 liter flask. From that reading, It doesn't talk about these two. So we're at 0. So which reaction is going to be favored?
Well, it says we have 0.25 moles of Cl2, right?
At what?
Oh, I see. Okay.
That's what I mean. Like, yeah, this gets tricky and wordy and stuff like that. So yeah, we all have to keep an eye on each other on this one, kind of. So, which of the reactions is favored at the start? Forward, because we don't have any of this, right? So an equilibrium is established in which 0.25 moles of Cl2 is present. What are the equilibrium concentrations of PCl5 and PCl3? All right, so if we take a look, we've got plus x, minus x. We have 0.40 minus x at equilibrium. We have x at equilibrium, and we have 0.25 at equilibrium. What does that mean x is equal to?
0.25.
0.25. So this is 0.4 minus 0.25. The concentration here is 0.15, 0.25, 0.25. We know K sub EQ equals products over reactants. So 0.25, 0.25 all over 0.15. 0.25 squared divided by 0.15. So we get 0.417 or 0.412, I believe. Or I'm sorry, 0.42. Again, K sub EQ does not have units. Questions there? All right. When 4 moles of HI are placed in a 5-liter container, equilibrium is established at 475 degrees Celsius. Once equilibrium is reached, there are 0.442 moles of I2. What is K sub EQ? So K sub EQ, remember, is products over reactants. Here we have our reaction. Our initial concentration is 4 moles per 5 liters. So 4 divided by 5. That's starting concentration. Do we have any of these? No. So they are 0. Change. As change occurs, we are going which reaction is favored? Forward. So we're going to plus x and minus 2x. Minus 2x because the coefficient here is 2. So this is 0.80 minus 2x. This is going to be x, and this is going to be x. It says once equilibrium is reached, there is 0.442 moles of I2 present. So in reality, instead of being x, this is 0.442 moles of I2. Right? These are concentrations, so these are molarities. So 0.4 divided by 5. Since this is 0.442 moles of I2, we actually have to divide that by 5 as well. 0.442 divided by 5. 0.0884 concentration, right? So if this is the concentration of this guy, that means that this is what? Same. And then we basically need to multiply that by 2. 2 times 0.0884. 0.8 minus 0.1768. So we get 0.6232 for the reactant. Remember, we are going to square that, and we'll get 0.0884 for the product. We are going to square that as well, because it's x and x right here. Point 0.0884 squared. 0.0884 squared divided by 0.6232.
The answer is 0.0125394.
0.0125. Right? Check it. Recheck the watch. It doesn't do squares and stuff like that already. 0.84 squared divided by 0.62. Yep, yes, got it. Questions there? Oh, wait. Look at that. You guys didn't catch me. I told you guys I was terrible at math. We got to square that guy too. There we go. 0.032. Oh, wait. The answer the other. 0.0884 squared divided by 0.6232 squared. 0.0201. So why did I have to square that? Because up here. Remember, this right here is not that squared. That is just the concentration of it. So from the formula, we had to square that too. Why was this squared? Because we had the concentration of H and I, and they were equal. Okay, I want to show you one where you actually have to use the solver function, but I don't know if we're going to get there. Let's do number 4 here. I think number 4 will get us there. Try number 3 on your own tonight. For the system 2A, so we have our reaction. 2A yields 2B plus C. Case of BQ equals 2.6 times 10 to the negative 6th. We have B squared times C squared. Apparently people want to add these. Keep in mind that just because that says plus, we actually do multiply these. And so that is a common mistake for people, was to try to add these or whatnot. A squared, yeah, you don't want to start putting that in, because the math on this is silly enough whenever it comes to all the squaring and stuff like that, and making sure these coefficients match up. So our initial concentration, 3 moles of A put into a 1.5 liter flask. 3 divided by 1.5. And if we take a look here, we don't have any B and we don't have any C. So those are both 0. What's our change going to be for this one?
Minus 2x.
Minus 2x. Change for this one. Plus 2x. See, this is where I don't know. Like, I look around and then I see like some blank stares, and then I hear the way that you guys say it to me. It just seems like condescending. Like, we know, don't you want to? Like, I just want to make sure that we're all on the same page here. C plus x, right? If you're not seeing this, all I'm doing is I'm sitting there saying that the initial concentration of this may be 2. That's not why this is 2. It's 2 because of this. We're going to use up 2 moles per liter of this stuff to make 2 moles per liter of this stuff and 1 mole per liter of this stuff. The reason we're doing that is because of Le Chatelier's principle. We don't have any of this stuff. If this reaction is to take place, it has to make some of this. So it has to go forward. For every whatever it goes forward, it uses up 2 moles of this, and it makes 2 moles of this and 1 mole of this. I mean, that's the chemistry behind it, right?
Confused on where you got the 2 from in the initial.
Yes. So, and this is the 3 moles of A per 1.5 liters. So that is molarity moles per liter. So we take 3 divided by 1.5, which is 2. So at equilibrium, what's this going to be? This is going to be 2 minus 2x. This is going to be 2x, and this is going to be x. That is their concentrations at equilibrium. We know that this is 2.6 times 10 to the negative 6. So we need to take 2.6 times 10 to the negative 6 equals b, which is 2x, and we're going to square that. C, which is x, and then a, which is 2 minus 2x squared. The top, 2 squared is 4x squared times x is 4x cubed. And then the bottom is 2 minus 2x, and then the quantity squared. Now here's the deal. We can set this equal to 0, and we can take 2.6 times 10 to the negative 6. If you want, you can have a heyday of math on this, right? But these calculators have a function called the solver. So we're going to try to use that. Hopefully I can do this, right? So grab that calculator, and you're probably going to want to try this like 6 times a night. Again, they actually said on one of the videos that you don't have to use the quadratic formula on the AP final, but you do have to be willing to do all the factoring stuff. If you can use the calculator to do this, and you have the calculator ability with you, then you don't have to do that. Up to you, right? So if you hit math and you hit up, and it comes to solver function, you want to get it to where it says an equation. Notice I've set this equation equal to 0 by subtracting 2.6 times 10 to the negative 6 from both sides. Huge ton of parentheses here. So I'm going to start with 2 just to make sure. It may not be enough. I'm going to add some more. But there I'm going to put 4, and then I'm going to use this button right here, which is XTO on it, or XT theta. And then I'm going to cube that. If you guys use this before, I'm going to waste my time. You guys know how to use it. No. I just want to make sure. So there is 4x cubed. I'm going to end the print. Oh, yeah, I'm going to end the parentheses on that. Now, if I did this one, I would put all of that in a different parentheses. So make sure you realize that I've already done some. Did I do some factoring there? I already combined these two terms. Another math teachers would sound a lot cooler when they do this. But 4x cubed, that's in parentheses. So I'm going to divide, and I'm actually going to need another parentheses over here. I'm going to insert another parentheses over there because I want to divide this parentheses 2 minus 2x, and I'm going to square that. Now I'm going to end the parentheses here so that this is one thing. So this right here is currently saying 4x to the third divided by 2 minus 2x squared, and that's that end of that parentheses. So I've got one more parentheses to end. You can always count them up. 1, 2, 3, 4. 1, 2, 3. So I've got one more parentheses to end. And that's going to be the minus 2.6 times 10 to the negative 6. And that, hit enter. Now here it says, okay, give us an x, smart guy. I'm going to give it an x of 0 because you can never have a negative case of EQ. You can never have a negative concentration or a negative pressure, right? These things don't exist. When you're solving for the quadratic equation, you know that when you square things and stuff like that, you can have plus or minus, right? 7 squared is 49 and negative 7 squared is 49. We don't care about the negative term because you cannot have negative concentration and all this stuff. So we give it a suggestion of 0, we hit enter, and then we go back up. Now this is the key part. This is where people make mistakes. If you look down at enter, above enter is a little word called solve, and it's in green or whatever. If you got a fancy TI, whatever it is, it may be different. I don't even think that any of mine had that. We actually had to do the quadratic formula 20 years ago. So you guys are lucky on that. You need to hit the alpha key instead of the second key and hit enter there. And then it will think for a minute, and then it will give you an answer. X equals 0.0136, right? So then we can actually put 0.0136 for X. And then here we would have 2 times 0.0136. And then 2 minus 2 times 0.0136. So there are your concentrations at equilibrium. Do these make sense? Now look, our case of EQ is times 10 to the negative 6. Does it make sense then? If the case of EQ is times 10 to the negative 6, that means we are favoring which product or reaction? Is it greater than or less than 1? Less than 1, so we are favoring reactants. Do we have a higher concentration of reactant? Is 1.97 greater than 0.2? Yes. All right. So for tomorrow, I'd like for you to try, this is big, try 2, 5, 6, and 7. Some require the solver, some require the rice table, some don't. That's why it's weird and you have to think a lot. Questions from home viewers?
My calculator required a second equation. Is it just 0 or?
Yes, it is just 0. If you've got the fancy dancy ones, you could have actually, instead of subtracting the whatever from both sides, you could have put that on the other side of the equation. Was that just a snide way of telling everybody that you've got a better calculator than that? No, I'm just kidding. Hayden, you've got one that, yeah, right? You know how to use all that function stuff?
Usually I just graph it.
Hayden just graphs it. So if you want to do that, you can do that too. Is it better? Is it quicker or what?
It can be, and it's easier to find like multiple values because you can just plug them in.
All right, so that's way above my math pay grade. If that interests you, you might want to talk to Hayden. But yeah, I mean, math was my worst subject probably in high school, besides English. So I don't know what he means when he says graphic, guys. Seriously, if you want to, you can talk to Hayden about that. I'm assuming that you put it into y-intercept form and then just graph it. Is that what you're talking about?
Well, it doesn't. I mean, you can just find the equation and plug it in, like to y equals.
The y equals, there you go. Cool. Get out of here. Get to your second period class. Feel better, those of you that are sick, and wake up, those of you who are sleeping. Diego, how are you? Oh, he's gone. Have a great day, guys. Yep. That is about as close to the difficulty of math that we get. But there is something in acid basis that's a little bit more difficult. So if you can handle that, you can handle the rest of it. Yep. Bye.